Hi! I hope you've played around with the model a bit. Hopefully, you managed to create a better model than the one we showed. Either way, I am sure you had a lot of fun. I guess you were repeatedly hitting above the 97.5% mark. Maybe some of you even reached 98%. But does that mean that the model was 98% accurate? If I'm asking, that's obviously a tricky question. No, it doesn't. That's the validation accuracy. We must still test the model on the test dataset because the final accuracy of the model comes from forward propagating the test dataset, not the validation. The reason is we may have overfit. But didn't we already deal with overfitting? That's a fine point, as some of you could miss the difference between validation and test datasets. So let's clarify that. We train on the training data and then validate on the validation data. That's how we make sure our parameters, the weights, and the biases don't overfit. Once we train our first model, though, we fiddle with the hyperparameters. Normally, we won't change only the width of the hidden layers. We can adjust the depth, the learning rate, the batch size, the activation functions for each layer, and so on. You've probably done it all. Each time we make a change, we run the model once more and check if the validation accuracy improved. After 10 to 20 different combinations, we may reach a model with outstanding validation accuracy. In essence, we are trying to find the best hyperparameters. But what we find are not the best hyperparameters in general. These are the hyperparameters that fit our validation dataset best. Basically, by fine-tuning them, we are overfitting the validation dataset. Let's elaborate a bit. During the training stage, we can overfit the parameters or the weights and biases. The validation dataset is our reality check that prevents us from overfitting the parameters. After fiddling with the hyperparameters, we can overfit the validation dataset, as we are considering the validation accuracy as a benchmark for how good the model is. The test dataset, then, is our reality check that prevents us from overfitting the hyperparameters. It is a dataset the model has truly never seen. Well, let's test the model then. We can assess the test accuracy using the method evaluate. So, if we write model evaluate test data, we will be forward propagating the test data through the net. With our current model structure, there would be two outputs, the loss and the accuracy, the same ones we had in the training stage. To make it clearer, I'll store them in test loss and test accuracy. Let's run the code. Nothing comes out as we still haven't displayed them. Let's print the results using some nice formatting. Here's the result. Our model has a final test accuracy around 97.5%. This is also the final stage of the machine learning process. After we test the model, conceptually, we are no longer allowed to change it. If you start changing the model after this point, the test data will no longer be a dataset the model has never seen. You'd have feedback that it has around 97.5% accuracy with this particular configuration. The main point of the test dataset is to simulate model deployment. If we get 50% or 60% testing accuracy, we will know for sure that our model has overfit and it will fail miserably in real life. However, getting a value very close to the validation accuracy shows that we have not overfit. Finally, the test accuracy is the accuracy we expect to observe if we deploy the model in the real world. Great! This was our last lecture on the MNIST data. In the next section, we will take a real dataset, pre-process it, and solve a business case. Can't wait to see you there! Oh, and thanks for watching.